Okay, so we have finally come to some group theoretic exercises. Although these first preliminary ones don't exactly involve any general group theoretic things which are yet to come, but they start with permutations. And in this one, we are given two permutations, sigma and tau, in S4. S4, you recall, is the system consisting of all the bijective maps on this set, that is one-to-one onto mappings from this set to itself, along with the operation composition of mappings. So two such permutations, two such functions are given, sigma and tau, and we already know what these symbols mean. This symbol, for example, it represents a function sigma which maps 1 onto 3, 2 onto 1, 3 onto 4 and 4 to 2. Like that we have tau. Now we have to calculate these compositions and we have to also find the inverse of the permutation sigma. So let us first calculate this one. Since for this one, let us show all the details. This is what sigma of tau of 1. Tau of 1 is 3, so that means this is sigma of 3, and sigma of 3 is 4. Like that we calculate the composition at 2. Tau of 2 is 4. And sigma of 4 is 2. Then sigma composition tau of 3, that is sigma of tau of 3. Tau of 3 is 1, that means this is sigma of 1, which is 3, and sigma composition tau of 4 is sigma of tau of 4. Tau of 4 is 2, so this is sigma of 2, and sigma of 2 is 1. Since we have these things, so we have sigma composition tau. We can now use this notation, and in the second row we will write those outputs, the images. So the image of 1 under this composition is 4, so we write 4 below 1. Then the image of 2 is 2, the image of 3 is 3, and the image of 4 is 1. So this is our sigma composition tau. Like that, next we calculate tau composition sigma, and this time we are not going to show all these calculations. We can speed things up by doing the calculations mentally, which is not very difficult. I mean, you can see, let us see what we are going to write here. we straight away write like this. So now we have to calculate tau composition sigma. So what you do, you use these notations and write tau composition sigma like that, using that notation. So tau is this permutation 3412, and then we write sigma 3142. Because of the way we are calculating things, we first apply tau and then we apply sigma. So here also we will start our mental calculation like that. We first, okay, this one is tau composition sigma. So first of all we will apply sigma, and then on the resulting thing we will apply tau. So what will this product or this composition do to 1? This is sigma. Sigma takes 1 to 3, and then tau takes 3 to 1. That means the composition takes 1 to 1 back to 1. It does not change 1. Like that, 2 to 1, 1 to 3. That means 2 to 3. 3 to 4, 4 to 2. So 3 to 2. 4 to 2, 2 to 4. So 4 is unchanged. So this is our tau composition sigma. So we did not have to write these equations. And for number 3, we argue like this. The inverse of sigma is, okay, I think this much space is enough. 1, 2, 3, 4. So sigma takes 1 to 3, 2 to 1, 3 to 4, and 4 to 2. The inverse of sigma will do just the opposite. It will map 3 to 1, 1 to 2, 4 to 3, and 2 to 4. So that means sigma inverse maps 1 to 2, 1 to 2. Then it maps 2 to 4. And it maps 3 to 1 and 4 to 3. So that is the inverse of sigma. And you can quickly see that this is really the inverse, because if you compose these two maps, for example, then 1 is taken to 2 by sigma inverse, and then that 2 is taken back to 1 by sigma. So sigma composition sigma inverse takes 1 to 1. It does not change 1. Similarly, it also does not change the other 3 inputs. So that is why sigma composition sigma inverse is the identity map, and that is why this is the inverse of sigma. So that is the first one. Then exercise 2. It is similar. Instead of S4 we now have S5, and here there will be one more column in these symbols, and these of course will change. So here sigma is 53214, 53214, and tau likewise is also such a permutation. Two, 4, 1, 3, 5. Calculate the following. Here, however, the things we have to calculate are not simply like this. It is these things: sigma tau sigma, then sigma sigma tau. 3 mappings, and of course the third one is the inverse of sigma. So things will change here. Although we have 3 mappings in these first 2 products, we are not going to repeat this type of calculations, okay? Because you can see that whatever we did here with 2 permutations, we can easily do that with 3. We just have to write a little more. Okay, so let us start. Here we have sigma tau sigma is equal to, now we cannot possibly write this entire thing like this. We have to write like this. So this is equal to let's first keep this sigma and write this tau, the middle tau. In that we use this symbol. This is to save space. 2, 4, 1, 3, 5. And then we write that rightmost sigma now as this symbol. This one is 5, 3, 2, 1, 4. Okay. Now, for the sake of understanding, I am again keeping this sigma as it is, and let us now calculate this product first, like how we calculated previously. So 1 goes to 5 and 5 then again goes to 5. So 1 to 5. 2 to 3, 3 to 1. So 2 to 1. 3 to 2, 2 to 4. So 3 to 4. 4 to 1, 1 to 2. So 4 to 2. And 5 will go to 3. But anyway, let us also see here directly. 5 to 4, 4 to 3. Yes. And now again here we write sigma. For 5, so it is 5, 3, 2, 1, 4. And this one, when we write to the right of this, 5, 1, 4, 2, 3. One to 5, 5 to 4, 1 to 4, 2 to 1, 1 to 5, 2 to 5, 3 to 4, 4 to 1, 3 to 1, 4 to 2, 2 to 3, 4 to 3, and this one will be 2, 5 to 3, 3 to 2, yes. And lastly, let me just see whether I have written it correctly. Sigma tau sigma 24135 and 53214. Yes. So this is our sigma tau sigma. Like that, the second one, sigma sigma tau. This time let us just do the sigma sigma first. Okay, and it does not matter which one you decide to do first. Here we have calculated tau sigma first, and then we have considered the product of that with sigma. But if you decide to calculate sigma tau first and then take its product with sigma, you are going to get the same thing. That is because of the associative law. Function composition is associative, which we already have seen in precisely theorem 1-2. Okay, so here we decide to do this two first. So our sigma is like before, 1 2 3 4 5 5 3 2 1 4. And again this one. These notations, although convenient in showing exactly what the function is doing to all the inputs, is still a little cumbersome. The better notations are coming. Okay. When we learn about permutations more, we will see that one can write permutations as products of some things called cycles. That is much better. So we carefully calculate the first product, 1 2 3 4 5, and I already need ink. If you want, you can go this way also, although I would not advise doing that, because it's good to have the habit of doing the calculations like this from the right side to the left side. Why it will not matter in this case, that's because the two things are the same. I mean, what I am saying is that if you want, you can see like this, 1 to 5, 5 to 4, so 1 to 4. But it is advisable not to do that. Okay, it will only create more confusion. So we continue our calculation like this, from here to here, 1 to 5, 5 to 4. You are going to get the same thing, 1 to 5, 5 to 4, so 1 to 4. Then 2 to 3, 3 to 2. So 2 is unchanged. 3 to 2, 2 to 3, 3 is also unchanged. Okay. 4 to 1, 1 to 5, so 4 to 5. And 5 now has to go to 1. 5 to 4, 4 to 1, yes. Why am I saying that the last output has to be the one which has not appeared before? That is because The product itself also has to be a permutation. We have already proved that. That when you take the product or the composition of two bijections or permutations, the resulting mapping is also a permutation. So that's why we are able to say that the last output would be the one which has not appeared before. Okay. 1, 2, 3, 4, 5, 4, 2, 3, 5, 1. And then tau, which is this one. Anyway, let me just see. 1, 2, 3, 4, 5. 2, 4, 1, 3, 5. Yes. One to two. 1 to 2. 2 is unchanged, so 1 goes to 2. 2 goes to 4. 4 goes to 5. So 2 to 5. 5 is unchanged. 5 goes to 1. Oh, wait. Not yet. 3. Now comes 3. If you want, you can do in any manner you want, but it's good to maintain an order. 3 to 1, 1 to 4. So 3 to 4. 4 to 3, and 3 is unchanged. So 4 to 3, and then 5 goes to 1. In these calculations, these products, if it happens that in the second row a number is repeated, that automatically tells you have made a mistake, because in then it's not a permutation, not a bijection. So this is the second one. And for the third one, we can just like before, we can write the inverse of sigma directly. The inverse of sigma is okay. So this is our sigma. So sigma inverse would take 1 to 4. 2 to 3. 3 to 2. 4 to 5. And 5 to 1. The original permutation is from bottom to top. For the original permutation, these are the inputs and these are the corresponding outputs. In that notation itself, if you see from bottom to top, oh, I just now said from bottom to top. No, in the original permutation, it's from top to bottom, input output. In that notation itself, if you reverse the order, if you go from bottom to top, then you get the inverse. Okay, so this is the inverse, and that completes the solution. Next, the third one. How many permutations are there in Sn? in Sn. In S5, how many permutations alphas? That is okay. In S5, how many permutations alpha satisfy this condition? That is, the image of 2 under alpha is 2. That is, alpha fixes 2 or does not change 2. Let f be any element in Sn. That means f is a permutation on the set of the first n natural numbers. Then f is a bijection from this set to itself. Okay. Now f of 1, that means the image of 1 under f, is any one of these, because it's a bijection from this set to itself. There are n choices for f of 1. We are not saying what f is precisely, we have just taken f to be any permutation on n symbols. So f of 1 has n choices, it can either be 1 or 2 or 3 like that, all the way up to n, any one of these. So there are n choices for f of 1 corresponding to each such choice there are n minus 1 choices for f of 2. Once you have chosen f of 1, say you have chosen f of 1 to be 3, okay, then f of 2 can be any one of the remaining numbers, that is all these numbers except 3. F of 2 at the same time cannot be also 3, because then f would not be 1 to 1, it will be 2 to 1 or many to 1. So that's why we are left now with n minus 1 choices for f of 2. So there are n times n minus 1 choices for f of 1 and f of 2. Okay, because your choice f of 1 equal to 3 brings with it n minus 1 possibilities, and that is only for the choice f of 1 equal to 3, but f of 1 itself can be chosen in n different ways. So together you get n times n minus 1 different possibilities of choosing f of 1 and f of 2, and corresponding to each such choice of f of 1 and f of 2, f of 3 then can be chosen in some ways. f of 3 can be chosen in n minus 2 ways, because f of 1 and f of 2 have already been chosen, so they have each one of them has captured one value from this set. So we are now left with n minus 2 possibilities, free values to be taken by f of 3. So there are n minus 2 ways now available for getting f of 3. Thus f of 1, f of 2 and f of 3 can be chosen in n times n minus 1 times n minus 2 ways. Proceeding like this, we see that f of 1, f of 2, f of 3 and so on, f of n can be chosen in this many ways: n times n minus 1 times n minus 2 times 3 times 2 times 1, which you also write as n factorial ways. Hence the number of permutations in Sn is n factorial. That many permutations we will have in, or that many elements we have in Sn, which are nothing but permutations. Okay. Now in S5, how many permutations satisfy this? So that means now alpha is a permutation in S5 where alpha of 2 has already been chosen and it is fixed, it is equal to 2, it is nothing else. Then you have to decide what the other outputs can be. Okay, let alpha belong to S5 such that alpha of 2 is 2. Okay, so because we are in S5, there are 5 symbols. Since alpha of 2 has already taken one symbol, so for alpha of 1 there are 4 symbols remaining, 4 free symbols yet to be taken. So there are 4 choices for alpha of 1. Corresponding to each such choice there are 3 choices for alpha. Don't write alpha of 2. Okay, alpha of 2 has already been chosen and it is fixed, it is equal to 2. 3 choices for alpha of 3, and then proceeding like this, because we have written the argument once in the general case, so we can now be somewhat sketchy. So continuing like the above paragraph, this one. We get that the number of permutations alpha in S5 satisfying alpha of 2 equal to 2 is 4 times 3 times 2 times 1, which is 4 factorial, that is 24. Okay. If you want an example of this type of permutations, you can clearly see that these are, for example, 2 such permutations: 3 2 1 5 4 and 1 3 5 4. They are clearly permutations, and both of them fix 2. There are others like this. Precisely there are 24, so these 2 are from among those 24. And note one more thing, that the identity permutation, which does not change anything, that is also a permutation of this form, which of course also does not change 2, it fixes 2. Okay, next. Three, 4. Let H be the set of all permutations. Alpha in S5 satisfying alpha up to that same thing. Alpha up to is equal to 2. So that means the kind of permutations we were trying to figure out their number, that set is now H. So there are 24 elements in H. That's what we found here. Which of the properties we have discussed closure, associativity, identity, inverses does H enjoy under composition of functions? Okay, so we have to see whether each one of these properties is satisfied by H or not. It's not very difficult. Here we don't have to take specific examples like this and see what is happening. We can take general elements from the set H and see whether these properties are true. So let us start with closure property. Let alpha and beta belong to H. We have to see whether their composition belongs to H. If that is the case, then H is closed under composition of functions. Then automatically we have two conditions on alpha and beta. Since they are coming from H, each one of them fixes 2. Alpha of 2 is 2 and beta of 2 is also 2. Hence, what about the effect of their composition on 2? This is 2 and this one is also 2. So the composition also does not change 2, which implies the composition belongs to H. Thus, H is closed under composition of functions. There are some things to note here, okay, about this closure property. Alpha and beta, you notice this. Alpha and beta have been chosen from H. But H after all is a subset of S5. Precisely, it has those elements which fix 2. There are other elements in S5 that are not in H. Now, because we have chosen alpha and beta in H, automatically they are also in S5. And we already know from our previous theorems on bijective maps that alpha beta is in S5, but this is something else, this is extra. It is saying that, well, okay, this is your S5 and this is your H. Alpha and beta have been chosen from H. So being elements in S5, their composition is already in S5, that we know from previous theorems. But now we have shown that alpha beta is not only in S5, it's in particular in, more precisely it is in H. So this is extra. Okay, it does not follow from the things we did before, and that this fact is expressed by saying that H is closed under composition of mappings. So you take things from within H, compose them, you are going to be inside H. You cannot get out of H. H traps all the happenings from within itself in itself. Next, associativity. Let alpha, beta and gamma be three elements in H. Then they are also three elements in S5, and we saw before that in S5 composition of functions is associative, and that fact comes from theorem 1, 2. So we will refer to that here by theorem 1, 2. We have this, and that's what we mean by associativity. It guarantees, no matter how you calculate the product alpha, beta, gamma, whether you do this one first and then you take the composition of that with gamma, or you do like this, you are going to get the same thing. And this is in fact the thing that we used in some previous exercises, where we calculated, for example, this type of products. And in fact, this expression itself is meaningful because of this. The fact that it does not matter how one brackets the things, that makes this expression unambiguous and meaningful. Without associativity, this expression as it stands will be meaningless. Hence, the product, or we can just simply write like this, hence composition of functions is associative in H. And this is often expressed like this. I mean, we don't usually write this type of things. You can better understand this like this. Something called associativity happens all over S5. So automatically that will also happen in this smaller region H. If you have a cold country, for example, then a part of the country will also automatically be cold. That's the thing here. So usually we write like this, since function composition in general is associative and is true throughout S5, so in particular inside H also it is true. The identity permutation how shall I denote the identity? I forgot to see what the author is using to denote the identity permutation. Maybe he writes I or the Greek iota. I'm not sure. I haven't seen any special symbol to denote the identity permutation. If there is one such, then you please use that. Okay, I'm just going to write any symbol. The identity permutation, let me just write iota belonging to S5 belongs also to H, because it fixes, in fact it fixes everything, so it fixes 2 also. So that means H has the identity element of S5. Next, let alpha be any element in H. Then alpha of 2 is 2. This implies alpha inverse of 2. Are we allowed to use this notation now at this stage, or no, we can allow this notation, no, because it is simply the inverse function of alpha. Yes, since we are still dealing with functions and not general group elements, so we can use this notation. It is the inverse function, that's all. So the image of 2 under the inverse function of alpha is also going to be 2. Alpha does not change 2, so it's like this, no? You take, say your alpha is this. This is your alpha. Now if you calculate alpha inverse like that, like how we were calculating it in a few of the previous exercises, 1 to 3, 2 to 2, 3 to 1, 4 to 5, 5 to 4. Oh, so in this case alpha inverse and alpha are actually identical. Anyway, so the point here is that the thing to observe here is that since alpha does not change 2, alpha inverse also does not change 2. In alpha we come from top to bottom, in alpha inverse we come from bottom to top here, okay, not there. So that is why 2 remains unchanged by the inverse also. Hence alpha inverse belongs to H, that is the inverse of every element in H is again in H. So you see that whatever properties S5 enjoys, I mean these 4 properties, closure, associativity, identity and inverses, existence of inverses, these same properties are also enjoyed by this smaller set H. You take any 2 elements in S5, compose them, the product is in S5, that is the closure property. In particular, you are taking elements from H and composing them. That composition belongs to H. So H also satisfies the closure property. Satisfying associativity is almost trivial. Associativity is true throughout S5. So in particular, that is also true for elements coming from H. The identity element in S5 is the identity mapping, which in particular actually is residing inside H. And the fourth thing is that if you take an element from H, then it will have an inverse, and that inverse actually is the function inverse, because your element is a function which is a bijection, so there is an inverse. That inverse in particular, because your original element is coming from H, it has been found that the inverse also is in H, and that same property is enjoyed in general by S5. So all those things are happening in particular in this localized place H. Okay, so all of them. These properties seem very easy. They are somewhat easy, although easy is a subjective term. Still, they are quite easy, much easier than some other such properties we will come across in algebra. But in spite of this easiness, they give us a lot. In fact, using this property, we can measure symmetry in anything. What comes on your mind when you see this word symmetry? Saying that something is symmetrical, it is roughly something like this, that if it's about a geometric figure, maybe there is an axis such that with respect to this axis, the two halves are mirror images of each other. That is a kind of symmetry. In physical theories, except a few, you can take the equations and change the direction of time. In place of t, you can write minus t, and the equations don't change. That is a symmetry. That symmetry tells us that those theories do not distinguish between the forward and the backward direction of time. A theory that in fact distinguishes these two is the second law of thermodynamics, where the forward direction of time is that direction in which entropy tends to increase. So that is asymmetrical. Okay. There are many different types. I mean, you have a general idea of what symmetry is, and these four somewhat quite abstract still. As yet, these four properties of closure, associativity, existence of identity, existence of inverse, these things will give us a system which is known as group, and group theory is the study of symmetries. Okay. We will see more on these things when the time comes. So let us now go to this one ends here. The next one. The next one is the fifth one. Consider the state of all functions. Okay. consider the remaining exercises will be like this one. All functions from this set to that same set which of the properties does this set enjoy under composition of functions? Does this set enjoy under composition of functions? There is a high chance of making a terrible mistake here in this problem if one is not careful. You see, when we deal, as we deal more and more with this type of exercises, the general tendency is to assume the moment you see a set like this and some functions are being considered, you automatically assume they are permutations. Not necessarily. You see what is written here: consider the set of all functions from this set to itself. There are permutations among such functions, but there are also such among these functions there are also functions which are not permutations. Okay, so we are considering the set of all functions. How many of these properties are which one of these properties are enjoyed by this set? This is a much larger set than S5. S5 is a subset of this set. Okay, a proper subset in fact. So let us, for convenience, denote this set by something. Let S denote the set of all. There is a notation in mathematical literature for this particular set, but we can't use it here since it's not there in the text. Denote the set of all functions from this to this. okay, we have already started the solution. What the hell happened to me? Let alpha and beta be two elements in S. That means alpha and beta are functions from this set to itself, not necessarily permutations. Then alpha comma beta are both functions from this set to itself. So their composition is also a function from this set to itself. Why? That is because if you evaluate alpha beta at any input coming from here, say 3, then what is it? Alpha of beta of 3. Because beta maps this to itself, beta of 3 is again one of these numbers. On that, if you apply alpha, then you are again going to get something here itself, because alpha, just like beta, also maps this set into itself. None of these functions let us outside the set, so their successive application will also keep us inside the set. That's the thing. Hence, alpha beta belongs to S, that is S is closed under composition of mappings or functions, same thing. Composition of mappings is associative by theorem 1, 2, and this fact in fact does not depend on the type of the mappings. True, we consider composition of mappings associative, I mean we use it for permutations, but that is in general true. You recall the statement of this theorem. If you have mappings like this, I may be writing these sets, I mean there are some different notations here, maybe S is not there, but you can understand. Alpha is some mapping from set S to set T, beta is the mapping from T to U, and say gamma is the mapping from U to V. S, T, U, V, these are all sets. Then a part of this theorem says that their composition is associative. Which means this. Which means that these two functions, alpha composition, beta composition, No, we cannot take that, no? This will not make sense because of the way we are writing things, or because of the way we generally write things in mathematics. It should be gamma, beta, alpha. And another one is gamma, beta, alpha. Both are going to map S into V. Alpha takes us first from S to T, and then beta takes us from T to V, and then gamma takes us from T to U, and then gamma takes us from U to V. And we have to change the order. We have already discussed this before, but again I am saying we have to change the order because we write the input to the right side of the mapping name. If we decide to write it to the left side of the mapping name, then we don't have to change this order, which is what we do in Herstein's topics in algebra. Anyway, so this theorem says that these two compositions actually are the same thing, and that is our associative law. And in this theorem, there is no condition on this map that the maps have to be, for this particular part, the maps have to be one-to-one onto. No, they are just in general maps. So that's what we have written. Composition of mappings is associative. So the associative law is true in the set S, in our set S. So this is also true in S, the set of all functions from this set to itself. Okay. The identity function on the set obviously belongs to S. Why? Because the identity function is of course a bijection, it's a permutation, but after all it's a function, no? So since in S we have all such functions, so the identity also, like any other such function, is an element in S. So far the first three properties are true in S, despite the lack of the lack of one-to-one-ness and onto-ness, or both. But the next one is not necessarily true. Let alpha belong to S P given by, or let us use another symbol. Let delta belonging to S be given by this. Delta of 1 is equal to 1. Delta of 2 is also equal to 1. Delta of 3 is also 1. In fact, we decide to make all these images equal to 1. Where are we? 5. So 5 symbols. And by theorem 1-3, okay. No, theorem 1-3 does not say that this function does not have an inverse. The thing it says is that if we are given a bijective function on a set, then that function has inverse. Non-bijective functions have inverse that is not included in, they don't have inverse, that is not, that fact is not included in theorem 1-3. So anyway, we can argue specifically for this example, this function. Suppose there is an inverse we have taken delta, no? So let us take epsilon next. In S of delta, that is there is a function on this for which instead of writing for which, let us write such that delta composition epsilon of x is equal to x, and that is also equal to epsilon composition delta of x for all x belonging to this set. Okay. Now we are expecting a contradiction from this situation. Now what is that contradiction? It is something very obvious. What will it be? Delta of 1 is 1, okay, and epsilon of that 1 is going to be equal to 1, right? But delta of epsilon of 1. Oh, so if that means if we take x equal, okay, what happens if we take x equal to 2? This part of the equation tells us that delta of 2 is going to be equal to 1, so epsilon of 1 is going to be equal to 2. Okay, yes. Then one is equal to, so we are taking x equal to, because these equations are true for all x, so we can take x equal to 1 first, and using this part of the equation delta of 1 is 1, so epsilon of 1 has been found to be 1. And at the same time, if you take x equal to 2, that also you can do, then that is also equal to epsilon of delta of 2. delta of 2 is also 1, so epsilon of 1 has been found to be simultaneously 2, and this is clearly false. This is a contradiction and proves that our supposition is wrong. Thus, elements in S don't necessarily have inverses. So S is closed under composition of mappings. Composition of mappings is associative in general, so that is true in S. The identity map is in S. However, when we come to inverses, that thing is not, there is no guarantee that if you pick one element from S, there will be an inverse. So that's where it fails. This type of systems where the first three of those four axioms, which ultimately are going to be used to define groups, they also occur in mathematics and they have a name, whether it is monoid or I forgot, okay, I'm not sure, we will see. Or semi-group, I don't remember that right now. Okay, so that's just the thing, and there is one more. Let G be the set of all permutations of N, okay. And one more thing before we go to this one, those elements in capital S which are bijections, of course they have inverses. The elements that are not bijections, none of them will have an inverse, which you can make sense of that, okay, if you think of it generally. Here of course we have taken one example because that's enough for our purposes, but in general you can take any element in S that is not a bijection, which is either not one to one or not onto or neither one to one nor onto. You can prove theoretically that it cannot have an inverse. Okay, so now in this one we are considering all permutations of the set of natural numbers. So the set of symbols of which we are considering permutations now is infinite. Which of the properties, again same thing, at first when one encounters group theory, looking at those four simple axioms, it seems that nothing much can come out of it, but you will be surprised, or you may have already been surprised because you have seen what the things are in group theory, that so much follows from only those four axioms. Which of the following properties: closure, associativity, identity, and inverses. Does G enjoy? Under composition of functions. Now I think Lee is consistently using the word function, not mapping, but they are interchangeable, they are synonymous, they mean the same thing. Okay, so now here instead of a finite set of symbols, we have the set of natural numbers. But the functions we are considering are again permutations, not all functions like this one, I mean unlike this one. So then we have to decide whether that set is closed, whether associativity is true. Now this one I am not going to write the solution formally, I will just give you the thing, I mean what we have in this solution. You take you first of course denote the set. Oh, the set already is being denoted by G. So you take two elements from G. So they are bijections, each one of them is a bijection on N. So your theorem 1, 2 tells you that their composition is also a bijection on N. So it belongs to G. So G is closed under composition of functions. Next you take any three elements in G. So each one of them is again a bijection on N. And since the general associative law is true for functions, any type of functions, so here that will continue to be true. If you are wondering that back when I took those three functions alpha, beta and gamma, I took care of the order in writing the product. Here I am not doing that. Why? It is because in the general case those sets S, T, U, V, they were any sets. Here however all those sets are equal to the set of natural numbers. So here you can in fact form any product. You don't have that restriction of looking at the sets and forming the product that makes sense. Here you can in fact change the order. You can form beta, alpha, gamma and write the associative law like this. These two things are not the same thing. Okay, the moment you change the order, that potentially becomes something different, but you can form the products. That's what I am saying. Anyway, the point here is that the associative law is also true in G. Identity. The identity function on the set of natural numbers is known to be a bijection. So it belongs to G. And if you take a function from n to n that is a bijection, then your theorem 1, 3 tells you that its inverse exists, that is also a function from n to n, and that inverse is also a bijection. That means the inverse also, for example here alpha is an element in G, then the alpha inverse, which denotes the inverse function of the function alpha, is again a bijection on n, so it belongs to G. So yes, again we now have all the four properties being enjoyed by G. The last property failed to be true here in case of that set of in general all functions, but restoring permutations or bijections has brought back that property. Okay, and you please try to write this systematically as a solution, and this ends this set of exercises. From the next set of exercises onwards, the proper group theoretic problems we will encounter. So with that, I end this video. If you want to say something about these things, you can write in the comment section below, or you can mail me here. At this address. And tomorrow we have real analysis, where we are, I believe, we have completed the things on sequences of real numbers. So we are going to start the theory of infinite series and their convergence of real numbers. And then we will see where we can go with that. So see you tomorrow. Until then, have fun with mathematics. This is me, Lucifer, signing off from a mathematical room. Have a nice night.